If it is a center 2, what is the term that we're expecting? That we're looking for something like this bk, x minus 2 raised to the kth power. Isn't that the definition of a power series of center 2, right? So we want to turn this one into that. And we're using this geometric series. Remember, 1 over 1 minus x is really came from the geometric series. X is a common ratio. And this is that common ratio in here. So you have to pull out x minus 2 here. Okay? So there's no x minus 2. So this is how you pull out x minus 2. X squared, let there be as x minus 2. X minus 2 there. What should be the number outside, such as the same as before? It was 1 minus x before. I want to have that x minus 2 right there. Then it's together is a positive 2, right? So don't I need a negative 1 in here, such that together is a positive 1. So if you expand it out, you go back to 1 minus x, right? So if this one changes to positive 1, it would look like 1 minus z. X1 plus, let me factor that out. Negative x squared, what is this? 1 plus x minus 2? Is that right? So it is not 1 minus z form, but it's not bad. Remember what we did about x squared down there, 1 plus x squared? We can do the same thing. It's negative x squared 1 minus x minus 2. How about that? Is that all right? Now it's in the form x squared, and we can take care of that later. And down there, that's your z. Okay? Then it's going to be negative x squared divided by 1 minus z. So I still be able to pull out the form 1 minus z, where z is not too bad. Linear shift of x in there. So this will give you power series at center where? 2. The one that we looked at it before was the power series at center at 0. That is only valid to where? To the right by 1 unit, to the left by 1 unit, right? That was all we have. All right, let's pass it to the next part. Negative x squared set outside, and 1 over 1 minus z changes to k going from 0 to infinity of z to the kth power, right? When you change from elementary function to power series, you have to put this condition, absolute value of z must be less than 1. Is that right? Geometric series. So you write that down to negative x squared, and going from 0 to infinity, what is the z there? Z is a negative x minus 2, right? That's our substitution z there. Z is negative x minus 2. So I substitute negative x minus 2 kth power, right? Yeah. And if I can change this x squared in terms of x minus 2, I can put them together in here, really turn it into a power series. So here's the next step. That outside changed in terms of z, and inside already simplifies and revealing the shape as a power series there. All right? So what is x? So that I can substitute it inside and here. The z is how this one is related, right? Let me write that down. Z is negative x plus 2, correct? And x is 2 minus z, is that right? So therefore that x squared, that x is replaced by 2 minus z right there. Correct? Yeah. All right. So what we have here is that if you apply the negative, we have the following: negative 4z plus z squared. So I'm going to do that in the next line. Right here. is multiplied by k going from 0 to infinity and -1, k and x minus 2, which is really z, right? Is that right? Okay. Now, this is a 3 terms, and this whole thing is multiplied under the absolute convergence. You can do this finite distribution. If it is infinite, you have to be careful with 3 multiplications. So we have -4, this whole thing multiplied. So value -1 to the kth power, x minus 2 to the kth power. That if you multiply this whole thing to the first term, this is what you get. Second term is a 4z, k going from 0 to infinity, -1 to the kth power, x minus 2 to the kth. And next one is z squared in there, k going from 0 to infinity. This one is multiplied. There's -1 to the kth power, x minus 2 to the kth power. Is that right? So I'm going to write individual series as more like a power series of bringing that 4 inside. So here's a k equals 0, infinity, there's -4 times -1, there's the kth power, x minus 2 to the kth power. That's one series. And second one, 4z is there, 4 is bringing in, and -1 to the kth power. That z is really x minus 2, right? And then we put them together with x minus 2, so what is that? X minus 2 to the k plus first power, right? K going from 0 to infinity. Is that right? And the third one is that this z, x minus z, z is x minus 2, so together with the kth power, it becomes k plus second power. So here's a k going from 0 to infinity, -1 raised to the kth power, x minus 2 to the k plus 2. So the 3 power series showed up, all absolutely converging, and within that radius of radius of 1 around 2. Okay? Our goal is that we're going to put them all together under the single power x minus 2 to the k and collect them. These are all shifted a little bit, right? So we're going to reindex it so that make it all look like x minus 2 raised to the k. So here, j is going to be k plus 1. Then it's going to be x minus 2 raised to jth power, right? So it's going to look just like that, x minus 2 to the kth power. It's in the same form. So let's write that. What is this part in here? J starting from where? 0 is going to 1 there, right? And if it is going to infinity, it goes to infinity. K is going to infinity, right? So this one, the 4 times the negative. What is k here? Is that j minus 1? If you solve this one for k? And this whole thing is now written as x minus 2 to the jth power. So now it looks like x minus 2 to the kth power and relatively written the center at the power. So let's do this one. Since it's going to be u substitution, what is u going to be? K plus 2, right? Then it's going to be x minus 2 raised to the uth power. So this one is going to be written like this. U starting from where? If k starts from 0, you start from 2 there, right? So go to infinity and -1 raised to, what is k here? U minus 2, right? U minus 2. But you know the minus 2 doesn't do the -1. -1 raised to second power is a positive 1, right? So adding and subtracting even number in the exponent of -1 doesn't really do anything. So this is simply -1 to the uth power. But this one, x minus 2, u, is as simply as that. Alright? Once you reindex it, you go back to everything in terms of k, right? Because it's a dummy variable. Individual terms is all just indexing. So you go back to k. K going from 0 to infinity, -4, -1 raised to the kth power, x minus 2, the kth power, plus. Second one starts from k going from 1 to infinity, and 4 times -1, k minus 1, x minus 2, the kth power. All the kth power, plus this one starts from k going from 2 to infinity, -1, k minus 2, but I'm dropping that minus 2, right? It doesn't do anything. to the negative 1. So it's x minus 2 raised to the kth power. All are exactly in terms of x minus 2 to the k, x minus 2 to the kth, x minus 2 to the kth. So you can bring them all together over a common index. So what was the common index of all three common indices? This one starts from 0. This one doesn't start from 0. It starts from 1, right? This one starts from 2. So 2 to infinity is the common index. Is that right? We can only put them together for 2 to infinity. Whatever is not belonging to the common index, we have to write it separately. So it goes like this. This one, the term that doesn't belong to common index is k equals 0 and k equals 1, right? Common index starts from 2 to infinity. What is the k equals 0? That is negative 4. Correct? When k equals 1, what do you get? Negative 1 becomes a positive 4 and x minus 2 to the first power. These two terms doesn't belong to the common index, so I set aside. How about this one in here? K equals 1, so I have 4. This is 1, it becomes 0, and negative 1 to the 0 is 1, so it's x minus 2 there to the first power. That k equals 1 did not belong to here. Once you set aside this term, everything from k to the infinity, all bring it together under the same summation. Going from 2 to infinity, everything has this x minus 2 to the kth power. Is that right? What is the first one? Negative 4 times negative 1 to the kth power. Second coefficient, plus 4, negative 1 to the k minus first power. The last one is plus negative 1 to the kth power. Everything is x minus 2 to the k is common. You can factor it out. It happens like that. So this one has negative 1 to the k, negative 1 to the k, and negative 1 to the k all in the common, right? You factor that out. So I'm simplifying this one. Negative 1 to the k, factor it out. So once I factor it out, it's a negative 4, right? Once that factored out, what do you get? Negative 4 again. Is that right? Because there's a negative 1 there. Negative 4 factored out, you have positive 1, right? So altogether is a negative 7. Okay, so I'm writing down here. First two terms are special. It's a negative 4 plus positive 8 x minus 2. But after that, we have nice pattern, k going from 2 to infinity. All this thing is a negative 7 in there, right? Negative 8 plus 1. I can put that negative on top of this negative 1 to the kth power. So negative 1 to the k plus 1, and there's a 7 out there, and x minus 2 raised to the kth power. All right? That's why they don't do that too. All right? They do that at 0, and it's simple enough. But I'm showing you that if you do that even at 2, this function here is defined everywhere, right? Not only at 0, but only at 2 and 3. You can go anywhere. You can pull this one out and write it as a power series centered at 2. Okay?